Okay, now let's see if we have another redox reaction. Let's take iron metal, react it with an acid. And let me tell you a little joke first. You've heard about people saying, wow, if you put iron nail in Coca-Cola, it will eat the nail. And you go, really? And they're implying, just think what it will do to your stomach. Well, guess what? It does nothing to your stomach because your stomach's not made of iron. But it is true, it's a redox reaction. We're going to show that you put iron with any acid, it will dissolve the iron or oxidize it and it'll become the cation. That's true. And so let's do that reaction. Because there is an acid in Coca-Cola, it's a weak acid, phosphoric acid, it's dilute. And so it will eat some of the iron. And so let's do this. We know this reaction will occur if iron solid is above H+. Because here the cation's H+. See? This is the only non-metal species we have on that table, hydrogen. And so hydrogen gas is the neutral form H2, and then H+, some acid, is the oxidized form. So let's look at our table and see if this will work. So here's our iron. Oh, and here's our H+. So sure enough, the cations below the neutral metal, just like we need if there's a reaction. So we know we have a reaction. So let's go ahead and do it. Let's erase this. And so the iron's going to become iron 2+, and it's going to react with the chloride, and we know this is H+, cation. Remember, in an acid, the cation is always an H+. And so these are going to come down to make a neutral formula. And then the hydrogen ion's going to come out as a neutral form. And on the table, the neutral form is H2 gas, elemental form. So, sure enough, this is a redox reaction and single displacement. And you'll see little bubbles in the solution because the hydrogen gas is going to bubble out. Okay, and now we have to balance. But I think it's balanced though. Nope. We have to put a 2 here, and now it's balanced. 1 iron, 2 chlorides, 2 chlorides, 2 hydrogens, 2 hydrogens. So we have to put that 2 there. And now we've learned an important concept. Let's look at the activity series. Let me tell you more about this one. Okay, we're going to put a line here. Okay, the metals above hydrogen are called active metals. And the reason they're called active metals, they'll react with an acid to give hydrogen gas and dissolve the metal or oxidize the metal. And it makes sense because here are the neutral forms above the cation. So any reaction above, these will stay as oxidations, and this will flip because it's starting as the acid, the H+, and we'll have a redox reaction. Where these metals down here are called noble metals. And noble means they will not react with an acid to give hydrogen gas. And you'll notice, so these metals are a lot more stable than the metals up here, as far as staying the metal under normal standard temperature and pressure. So sure enough, these are the jewelry metals. These are the ones you make jewelry out of. They're really pretty. Some of them are kind of rare, and they're very stable. So it's nice to have jewelry not getting oxidized, but staying the real pretty, shiny, lustrous metal. So once again, now you know these are active metals, and these are called noble metals. And of the noble right here, gold's the most noble, right? Because it's in the bottom. It likes getting oxidized the least. So any metal above will give hydrogen gas and a salt when it's in an acid. Okay? Now let's do that problem again. Let's do it let's do the half reaction method. You don't have to do it. You can do exactly how I just did it. And this way is not in the chapter, but let's try it again. let's take iron solid plus HCl. And we know there's a reaction because we know this is H plus, and the cation's below the iron in the table. So therefore, we know there's a reaction. Let's do the net ionic equation real quick without even using the anion. We'll use those half reactions, flip the bottom one, equalize the electrons and add them together, and then we've got a redox reaction balanced already with net ionic without the spectators. And this is more like you're going to do it in chapter 20 if you do a full chapter on electrochemistry if you take Chem 122. So let's write the half reactions from the table. We've got iron going to iron 2 plus 2 electrons. Okay, that's right out of the table. And then the acid one we flip. 2H plus 2 electrons give H2 gas. See that? And it's got to be 2H plus because H2 here. H2 gas, elemental hydrogen is H2. So therefore we need 2 protons and 2 electrons. And we're lucky here because it's already 2 electrons and 2 electrons lost and gained, so we don't need any multipliers. So we can add and we'll have the net ionic equation. And so we'll cancel 2 electrons from both sides. Algebra allows us to do that. We'll put our arrow to separate the reactants from the products. We'll bring everything else down. Iron solid plus 2H plus goes to iron 2 plus hydrogen gas. And we get the net ionic equation because the chloride's a spectator. And once again, I don't care the way you do it. You can either give me the net ionic equation on an exam or quiz, or you can give me the balanced molecular. The important part, I want you to know how to flip the right one, predict if there's a reaction, then balance. And once again, once you have the full redox reaction, you'll never see electrons because they canceled algebraically. Okay? Okay, we're done with that part of chapter 4. Okay, if you look on the outline, now we have to do 2 other topics in chapter 4. We have to do concentrations of solutions and solution stoichiometry. And this is where the math comes in chapter 4. This is an important area for math, for chemistry, because in chemistry we work a lot with dilute water solutions, with solutes dissolved in the solution. And in our body, you know, we have a lot of solutions dissolved in our fluids. And so we want to keep track of the concentration of solute dissolved in a solvent. And there's lots of ways to do that. In chapter 13, they show almost 90% of the ways you can keep track of the concentration of a solute in a solvent. And so here we're going to learn the most common one, called molarity. Molarity. And the way they write molarity, it's an italicized big M. And molarity equals, mathematically, an equation, moles of solute per 1 liter of total volume of solution. Okay, moles of solute per 1 liter of solution. And so the denominator here is the whole volume, the whole solution. Okay, and so you can't measure moles on a balance, but you can measure grams and then do a gram to mole conversion and then divide that by the total volume to get the molarity of that solution. So let's go ahead and do a simple problem with molarity. So let's go ahead and keep that equation up here. Okay. And so let's go to a balance and weigh out 20 grams of sodium chloride. Okay, 20 grams of sodium chloride. And we're going to dissolve that in enough water to get a final volume of 700 milliliters. That is not the initial volume of the water before we put the salt in. Because when the salt goes in and dissolves, if we put 700 milliliters in it first and then put in the salt, the volume is going to raise past 700 milliliters. So when you make a molar solution, you do what's called QS. You QS it. This stands for quantity sufficient. Quantity sufficient. You add, here's how you do it. We're going to take a volumetric flask. And it's going to say 700 milliliters on it. Okay, we learned these in the equipment quiz. And now it's got a top, and you can get a nice cap for it too, where it seals it really nicely. And there'll be a line on the neck. A volumetric flask has one line on the neck. And what it's saying with that line, once you add enough solution where the meniscus is on that line, you've got exactly 700 milliliters. And these are super accurate, so they're expensive. Because the neck's narrow, so you can read the meniscus very accurately. And so here's how you make a molar solution. You go ahead and put some water in the volumetric flask first before you add the salt. Because some salts, if you put them in first and put the water, they turn into cement called caking. And you can't get it, it'll take half a day to get in solution. So you always put a little water in first, but make sure that when you put the salt in, it's not going to go above the line. So you don't put too much. And then you go ahead and weigh out the 20 grams of sodium chloride, take off the top, and put it in. Okay, so water first, and then add the salt that you weighed. So now we got the salt in there, and then you mix it. Try to dissolve as much as you can. Okay? And sometimes you put on a stir plate with a Teflon stir bar to get it all in solution. And then once it's in solution, you might have to add some more water so it all goes in solution. You QS. We're going to take whatever it takes. You go real fast here when you get to the neck, add some more distilled water, and then you add it slowly with the squirt bottle because it goes real fast when it goes in the neck. And you keep squirt bottling water in there until you get the meniscus right on the line. You got to be careful because once you go over the line, you're gone. You've ruined your accuracy of your molar solution. So you can put it in the hood and let it evaporate for a day, get under the line and add some more water. That's ridiculous, right? And so now we have our solution, and now you can put a stir bar and go above and mix it more if you have to, but it's, you know, the final volume is 700 mils. So that's what QS means. At the end, you QS to the final volume in your volumetric flask. Add quantity sufficient of water to reach your final volume. So now let's do the math. That's how you make the solution. Now let's do the math. Molarity equal, this is an equation here. Molarity equal moles of solute. So let's just go ahead and do it. So here we're going to put the 20 grams of NaCl in the numerator of our equation because we know we can turn that into moles in one step. And we use molar mass. So let's go ahead and find the molar mass of sodium chloride. We do our vertical tally, and it's 1 times 23 for a sodium, and then 1 times 35.5 for a chlorine. So we add that together and get 58.5 grams per mole. So we go 58.5 grams per 1 mole. And these are all sodium chloride. So that's the numerator in moles now. We had to do some dimensional analysis, but now we're using the equation, and we've got moles in our numerator now with one-step conversion. And you're always going to have to do, they're not going to tell you how many moles because you got to weigh it on a balance first. You don't weigh moles. So you're going to have to do that conversion always in the numerator for molarity. And now the denominator, we want to get in liters. We want moles per liter. And so this is where you want to use the metric system. You know there's 1,000 milliliters in a liter. And so if you want to convert milliliters to liters, just do it in your head. Do that, just divide by 1,000, move the decimal point 3 spaces to the left. And so 700 mils, we go 3 spaces to the left because there's 1,000 mils in a liter, and it'll be 0.7 liters. So 0.700 liters of sodium chloride solution. That's our final volume. And now we have the correct units. We've got moles of NaCl per liter NaCl, and those are the correct units for molarity. So once we do this calculation, we'll have the molarity of that solution we made, and it'll be 20 divided by 58.5 divided by 0.7 equal. Because remember, whenever you go down on your calculator, we only want to push the equal sign once. So here we're going down, so it's divided by, and here we're going down again, so it's divided by. So it's 20 divided by 58.5 divided by 0.7, and that'll be the molarity of our solution. And let me get my calculator so I can give you the answer of that. Okay, I've got my calculator now, so let's calculate this molarity. So I've got 20 divided by 58.5 divided by 0.7. And we want 4 significant figures here because we have 4 significant figures given. So let me erase my vertical tally, and here's how we write this. We'd write it 0.4884 molar NaCl. Okay? And so on our bottle, once we pour that into the bottle to keep it as a stock, we'd sit there and label it like that, 0.4884 molar NaCl. We read the big M as molar. And what that means, it's telling we have, if we had 1 liter of solution, it'd mean we have 0.4884 moles of sodium chloride in there. Okay? So let's do another one in the book, because these are very important, so let's practice another one of these. We're going to do the practice exercise in the book on page 140. Practice exercise 411. Practice exercise 411 on page 140. And it states, calculate the molarity. So once again, we want to know molarity, and that's an equation. Made by dissolving 5 grams of glucose. So that's going to be in our numerator. We'll just put glue for glucose. In sufficient water to form exactly 100 mils of solution. So we're going to go 0.100 liters. Because we know we'll divide 100 mils by 1,000, and that's 0.1 liter. Okay? And now we just have to change the grams of glucose into moles of glucose. We have moles per liter. And this is C6H12O6. And if you do a vertical tally, we've done this before, there's 180 grams of glucose and 1 mole of glucose. So once we do that molar mass conversion, we have moles of glucose per liters of glucose. And that'll be the molarity. So let's get the calculator again. And we go 5 divided by 180 divided by 0.1. And they went 3 sig figs, so we get 1.32 molar glucose. And let's see what they got in the book, see if we match their answer. Well, I didn't do that right, did I? Let's see, what did I do wrong here? And when we do that math, we get 0.278 molar glucose. And we look at the book, and we get 0.278 molar. So once again, when we label that bottle containing our glucose solution, we put 0.278 big M glucose. Okay, let's do another important problem. Let's do another practice exercise in the book. We're going to backtrack a step. I guess not backtrack. We're going to do the next practice exercise 412. And it's also on page 140. It says, what is the molar concentration of potassium ion in a 0.015 molar solution of potassium carbonate? Well, potassium carbonate is K2CO3 because this is a 2 negative on the carbonate, so it goes here, and this is a 1, parentheses 1. So here's how you do this one. This is a soluble salt, because remember, all alkali metal salts are soluble. So we're going to take this and we're going to show it dissolved in water into ions as a soluble salt. So you know that the cation's K plus and the anion's carbonate. And so we're going to make K plus ions and carbonates as it dissolves and pulls apart. It's an aqueous ionic compound or salt. But now, if there's a 1 here, we need a 2 here. And remember, this is parentheses 1, so now we have a balanced reaction as it dissolves in water. It forms 2 moles of potassium ions and 1 mole of carbonate. So the original molarity, our original concentration is 0.015 here. And before it dissolves, our initial concentrations are 0.015, 0, and 0 molarity. And then as it dissolves, this is a fully soluble salt. And so here we're going to dissolve all of this. So we have none of this. This is the change. And when we're done, our final concentrations, this is gone because all of it dissolved. And this is in proportion, the way it dissolves in proportion to the balanced molar coefficients. See, this is going to be a plus x, and this is going to, this is going to be a plus 2x. And this will be a plus x for the change. And see, this was minus x, which this was our original x here. And so here, this is our x, so this is going to be twice 2 times 0.015. Okay, which is 0.030 molar. See that's our change, and it's plus. So 0 plus 0.03 molar, our final concentration of potassium, is going to be 0.03 molar. See that? And they didn't ask for this one, but this one's just x plus x, so it's going to be plus 0.015, but in just case they did, that'd be 0.015 molar. And so we're going to label it like this. Then they know that you can get the individual concentration of ions by using the X things. They're proportional to the balanced coefficients when it ionizes or dissociates. And so, but they're always going to label it like this on the bottle, and then they know you can do this if you want for final concentration of potassium ion, final concentration of carbonate. So let's see if we got the answer right according to the book. And 0.030 molar potassium. And this is why you've got to go ahead and do the dissociation equation and then look at the coefficient. If this is a 1 and this is a 2, the final concentration of this has to be twice the initial this. And this one's going to be the same concentration initial because they're both 1 coefficients. Okay? Okay, let's do another problem. Let's say we have a stock solution. Okay. And let's say it has a label on it. And let's say it says 0.15 molar sodium hydroxide. So this is a strong base, and we have a bottle full of 0.150 molar sodium hydroxide. And so now we're going to take out a small volume out of that stock. This is our stock. And let's say we take out 150 microliters of that solution. The question is, how many we'll say moles of sodium hydroxide did we take out? So how many moles of sodium hydroxide did we take out, or how many? And that's A. And then B, how many grams of sodium hydroxide did we take out in that volume? So whenever you're not doing a molar calculation, but they're giving you a molarity. So here they gave us a molarity. If they give you a molarity, you're not calculating it, this is going to be a conversion factor. And we're going to rewrite it as 0.150 moles of sodium hydroxide per 1 liter of sodium hydroxide. So whenever using it as a conversion factor, you go ahead and rewrite the molarity by definition. The numerator will be that number with moles of solute per 1 liter of solution. And then we can flip this as a conversion factor. It allows us to convert liters to moles, or if we flip it, we can convert moles to liters using that molarity. Okay? So once again, let's think in conversion factor mentality here. Since they gave us this and asked a problem, that is not our given. It's going to be a conversion factor. Here's our given, the volume we took out. And here's the importance. Here's what's important when you do solution dimensional analysis. Liters times molarity equal moles solute. If you multiply liters times the molarity, you'll always get moles of solute. And let's prove that. Okay, liters times, and let's go ahead and change this like we did up here, moles per liter. That's what molarity means. Oh, the liter is going to cancel. And then we'll have moles of solute. So this is one of the most strong unit factors we have in dimensional analysis to do solution math. Liters times molarity equal moles. So if they ever give you a volume something and you know the molarity, you can calculate moles in that volume really quickly by going liters times molarity is moles. So that's what we're going to do here. So let's go and answer this problem now. I'm going to erase the problem so I have room to write. So we're going to go to moles first and then grams. So let's write this up. Let me write this up here. So I take my given 150 microliters sodium hydroxide solution. And then before I can touch molarity, see, I'm going to go like this. I'm going to go microliters to liters to moles to grams. This is part B and this is part A. So here I'm going to use a metric conversion. Here I'm going to use molarity. And here I'm going to use molar mass. See, that's a nice flow for calculation, dimensional analysis, and solution. You can always go volume to moles with molarity, and then if you want to go to grams, you just multiply by molar mass. So let's do part A first. We take 150 microliters, and then we learned there's 1 times 10 to the 6 microliters in a liter. Okay, now we're in liters, we can touch our molarity conversion factor. And so in 1 liter of our sodium hydroxide solution, we have 0.150 moles of sodium hydroxide. And now we've got part A answered. So let's get out the calculator. And we go 0.15 divided by 1,000,000, 1 times 10 to the 6th, times 0.15. And we went 3 sig figs. So part A, the answer is 2.25 times 10 to the negative 8 moles of sodium hydroxide. So that means in that 150 microliters we took out of that stock solution, there's 2.25 times 10 to the negative 8 moles of sodium hydroxide. And that makes sense. We're taking a number here and dividing it by 1,000,000, and then times it by a small number, 0.15. Okay. Whoops. Let me do this one more time, make sure I did it right on my calculator. 150 divided by 1,000,000 times 0.15. And 1, 2, 3, 4, 5. Yeah, somehow I pushed that wrong. And we get negative fifth here. 1, 2, 3, 4, 5. Yeah, I didn't feel real comfortable at negative 8, so I pushed my calculator wrong. I entered 0.15 instead of 150. Okay. Okay, and now let's do part B. We'll just take the answer we have there, or let's just do one more step. That answer is already in my calculator. And now we want the molar mass of sodium hydroxide. So we do a vertical tally. 1 times 23, 1 times 16, and 1 times 1. And we get 23, 16, and 1. And that gives us 40. 40 grams per mole for sodium hydroxide. So here we go, 40 grams of sodium hydroxide per 1 mole sodium hydroxide. That cancels the mole there. And we get grams of sodium hydroxide. So we take our previous answer times 40 and get 9 times 10 to the negative 4th grams of sodium hydroxide. And my calculator, it's only giving me 1 sig fig, and we really want 3. We'll pretend this is significant, and I'll put a dot there. But I'm not going to worry about it right now. We should have 3 sig figs there. So on your calculator, if you've got 3 digits, go ahead and write it down. But it'll be around 9 times 10 negative 4th. Okay? And so the importance of this problem is that whenever we label a solution, whatever we do with it, we can always keep track of moles and grams of any solute if we need to by doing conversions. Knowing that molarity is a conversion factor and molar mass, we can go from moles to grams. And so this is one of the most important types of dimensional analysis in solution. You go from liters to moles to grams, using molarity as a conversion factor if it's given, and then the grams with vertical tally. So you got to get your brain trained in this new conversion factor molarity if it's given. It's a true statement, unit factor for that solution to do any conversion you want to with. Okay? Now, we're going to do some really practical chemistry. Lab chemistry. If you do research in a lab, or even prepare solutions for an educational lab to do, you have to make concentrated solutions for the students. Just the right concentration. And you have to make solutions from liquids and from solids. Because some things, the stocks are solids, like salts. You know, you have some sodium hydroxide pellets. They're a solid called lye in a container. Or your acids and bases, well, your acids are usually liquids, like hydrochloric, sulfuric acid, etc. They come as liquids. And so first of all, let's make a salt solution. Let's make some sodium hydroxide. Let's say we have a lab, and let's say, oh, we need to make 850 milliliters of 0.250 molar sodium hydroxide. So we want to calculate how many grams we have to QS up to 250 milliliters, right? That's what we're doing. So we want to calculate how many grams, because it's a solid, sodium hydroxide, that we have to QS up to 250 milliliters. Oh, 850 milliliters. I'm reading the wrong one, aren't I? And we want it to be 0.25 molar, so we can have it for the lab. So, once again, your volume's the given. Because we're going to go volume to moles to grams with molarity and molar mass. See, volume times molarity is moles. And so let's take our given volume, and we want to put that in liters. So I'm going to divide that by 1,000. And so it's 0.850 liters of NaOH. Okay? And now the desired molarity is 0.25 molar. And so I rewrite that. That is 0.250 moles of sodium hydroxide per 1 liter sodium hydroxide solution. That's my molarity. And so now I canceled the liters and I'm in moles. Oh, and then to get to grams is easy. We've done that a lot. There's 40 grams of sodium hydroxide per 1 mole of sodium hydroxide. And that's the vertical tally we just did a few minutes ago. So now we're in grams. So now we get out our calculator and we do the math. So 0.85 times 0.25 times 40 equals 8.50 grams of sodium hydroxide. Okay? And that makes sense because this is a quarter. Quarter times 40 is 10, and then 10 times this is 8.5. So now here's how we make the solution. We get a graduate cylinder, I mean a volumetric flask, sorry. This says 850 on it. Or if you don't have an 850 milliliter volumetric flask, I cheat and use a graduate cylinder. It's not going to be as accurate because the meniscus is going to be harder to read and be accurate to get it to 850. But for the lab, student experiments, or a lot of things, good enough. But let's pretend I have an 850. So I put some water in here. I weigh out my 8.5 grams. I dump it in here. And then I use a wash paddle to get all the crystals in the bottom. Stir it on a stir plate with a Teflon stir bar. And then I QS it right to the line. Make sure it's all mixed. And there I have it. And so before I put this out, I label it 0.250 molar NaOH. And it's 800 mils, because that's the volume of my volumetric flask. I can pour it in another container. So I want to put this label on there, because then whatever they have to do with that, they can track the molarity, the moles, the grams, whatever they need to do. So you have to label your solution with concentration, so when they do quantitative chemistry, they can do the proper calculations and get the results they want. So this is one of the most, whenever I make a solution in the lab from a salt or a solid, I do this calculation. Desired volume times desired molarity times molar mass. And that tells me how many grams I got to QS to that final volume, so I have enough solution for the lab. Okay, so this is really important calculation. And when you work in a lab, they make you make all your solutions a lot of times, and you don't let anybody else, if you're doing research, you use your own, so if they calculated wrong, they messed up their experiments, not yours. Okay? Now, let's go ahead and do a dilution problem. A dilution problem is where you have a liquid stock, you want to dilute it, it's really concentrated, you want to dilute it to a certain volume of a less concentrated. And so, let's do hydrochloric acid. Hydrochloric acid, you can get it in big gallon jars. And the most concentrated you can buy, HCl, is 12 molar. Okay? Because of the solubility, they bubble hydrogen chloride gas through water, and because of the solubility, you can't get over 12 molar, 12.0 molar. So this is how you buy stock HCl. And so, let's say we want to do an experiment, and they say we need 900 milliliters of 1.2 molar HCl. So I've got to make 900 mils of 1.2 molar HCl for the lab. And to do this, use a dilution equation. You go molarity initial times volume initial equal molarity final times volume final. And some people have different subscripts here. They'll go con here, molarity concentrated, con times volume con. That means the stock solution. Stock solution has to be more concentrated than your desired, or you can't make it. Equal molarity final, or dilute, times volume dilute. So there's different subscripts, but that's the dilution equation. Okay? So, this is your volume dilute, or final. That's what you want to make it to. So it's your initial volume is how much you're going to take out of here and dilute. That'll be volume concentrated. So your volume concentrated is how much you need to take out of the stock and then dilute to your final concentration, your final volume, sorry. So this is our final volume, the diluted volume. And this is our molarity dilute. Our desired molarities are the diluted ones. And our volume is our desired volume. And so these are given, see? And then this is given. This is the stock. This is molarity concentrated. So usually in this problem, you got to rearrange the equation with algebra. You are calculating volume initial. So you rearrange the equation. We all write it like your book, I think. Dilute times molarity con. Boy, I'm not doing too good here. I'm sorry, we want to get volume concentrated. Volume concentrated. I need a break, huh? Volume concentrated equal molarity dilute times volume dilute over molarity concentrated. So with algebra, we're solving for VI initial or V con, same thing. And then you're going to take this and just QS it up to your final your desired volume, you've got your solution. But let's go ahead and calculate how much we have to take out of the stock to dilute. And you'll notice our molarity is going to cancel there. The label's going to cancel. But we'll do the math with the number. And so since this is cancels, we're going to use milliliters here, because we don't sit there and dump in liter amounts. And it's okay to have your volume here in milliliters, because we're not using the liters here in moles per liter, because they cancel here, moles per liter. See, same type of solution. So here we can get away with keeping this milliliters. So we don't have to convert this to liters in this problem. So let me go ahead and get some room. And so Vcon equal molarity dilute, what's our desired molarity. Now I'm not going to worry about, well, I'll go ahead and put the M there, times volume dilute, 900 mils, because we can leave it in mils, divided by Mcon, 12 molar. And this is all HCl. And so you can see the molarities cancel. They're both molarity HCl. And now I'm solving for volume milliliters. So Vcon equal. So get out my calculator and calculate this. So 1.2 times 900 divided by 12. And I get 90. 90 milliliters. Okay? 90. So that's how much I've got to take out of that 12 molar stock. And so what I do, I get a volumetric flask. This has 900 on it. Or a liter graduated cylinder. And then you add acid to water like you oughter. So you can't put the acid in first. It'll splatter. It'll be too exothermic. So you put some water in here like you always do. And then you go ahead and dump in your 90 mils of stock. And then you QS right to 900 mils. And now you've got 900 mils of 1.2 molar HCl. So once you mix that, you'll dump it into a container. And you don't have to put 900 mils. It doesn't matter. Whatever we take out of there is 1.2 molar. So this is how you make a stock solution in a lab. This is the dilution equation, called the dilution equation. So whenever you do a dilution problem, use this equation. Okay? And usually you're solving for how much to take out of your stock to QS your final volume, and then you'll get your desired molarity at that volume. Okay? So once again, we did the math here. We solve for V concentrated. I usually put V initial. Dilute is, our desired is 1.2 molar times 900 mils we want of it, divided by our stock molarity, and that is 90. Okay? And so that means I get 90 mils of my stock, 90 mils of 12 molar, and QS it up to my desired volume. Okay? And usually on an exam or something, they're just going to ask you to calculate Vcon. How much of the stock do you need to take out of it to QS your final volume. So these are really important molarity problems we just did. How to make a molar solution from a solid, and how much of that we have to weigh out, and then QS to our final desired volume. Or how to make a stock from a liquid stock. A dilution problem using this equation. Okay, I'm going to take a break for a minute and be right back. Okay, let's do another practice exercise from the book using molarity. Let's go to page 141. And we'll do practice exercise 413B. We're just going to do part B. And it says how many milliliters, so I go question mark, milliliters, how many milliliters of 0.5 molar sodium sulfate. So I go 0.50 molar sodium sulfate. Solution are needed to provide 0.038 moles of this salt. So this is kind of the opposite problem we did before. Before I took a certain volume, I took those microliters out of a stock solution, and I asked you how many moles and how many grams are in that volume we took out. So this is the reverse. How much do I have to take out of some stock solution of this stock to get 0.038 moles of that salt? So you go, what's my given? And once again, if you have other numbers besides molarity, your molarity is not your given. Okay, your molarity is not your given. Always use molarity as a conversion factor if something else is given. So here our given's going to be the other number, 0.038 moles. So, and let's go ahead and label it sodium sulfate. Okay, and they want us to convert to milliliters. Okay, I want to go from moles to milliliters. So we can go from moles to liters to milliliters. See that? And this is going to be molarity. And this is just going to be a metric conversion. Because remember, with molarity, you can either convert liters to moles or moles to liters by flipping the conversion. And so now I'm going to use my molarity. I have to rewrite it. I want to cancel moles of solute and go to liters of solute. And so remember, it's always per 1 liter when you rewrite it. And here's the moles, 0.50. Let me see how many sig figs. Oh, only 2. And so now, when I flip that molarity given, using a conversion factor, I went from moles to liters. And now I just need one more step. We want to convert liters to milliliters. So there's 1,000 milliliters in a liter. So now I've got milliliters of Na2SO4, and that's what the question was asking. So I get out my calculator. And I go 0.038 divided by 0.5 times 1,000. I went 2 sig figs, 76 milliliters. And so let's see if we match the book's answer. And sure enough, 76 milliliters. So here I wanted to show you molarity as a conversion factor, either moles per liter or flip it, liters per mole. Because remember, that's a true statement for that solution. It's a unit factor, so we can use it as a conversion factor. So most of the stuff we're doing in solution, a lot of it, some of it's equation math, but a lot of it's dimensional analysis still. And remember that magic dimensional analysis, liter times volume, volume times molarity equal moles. Or you flip it, moles times molarity flipped equal volume. That gives us a lot of power to do quantitative chemistry with solutions, knowing getting concentrations, using concentrations of solute. Okay, and that's important because if you give an IV in medicine, you know you got to give the patient just the right amount of drug or IV or whatever, and so you got to know the concentrations, how many mils to give, the rate to give it, and so using this type of math, you can always calculate that. Okay. Okay, now we're going to finish the lecture on chapter 4 with the last section called Solution Stoichiometry. And since in the solution stoichiometry we're going to use a balanced equation, we can't do this calculation. You can't do solution stoichiometry without a balanced equation. And we're going to do what's called a titration. in a titration is called volumetric analysis. In the lab, we already did gravimetric analysis. There we used a balanced equation and masses, knowing gram amounts, to calculate how much of a certain thing's in a solid. Like we did plant food, remember? And that was using balances in solids. But here, we're going to find out the concentration of an unknown solution. We're going to know what the solution is, but we don't want to know the concentration. We don't know the concentration. So what we're going to do, we're going to force that solution undergo a reaction where we can balance the equation. And then we're going to react it with a new thing, and we're going to have a system where we know exactly when we consumed all the reactants. And that's called the equivalence point. The equivalence point of a titration is when you add just enough known to your unknown in a reaction, so you know that you consumed all of your unknown. Okay? So in your reaction, there's no excess reagent and there's no limiting reagent. And the reason why that's important, as soon as we know we're at the equivalence point, we know the mole amounts in our solution with the reaction are in proportion to our balance moles in the balanced equation. So once we know that, we can use the balanced equation to do math, chemical balanced equation stoichiometry. And so remember, when we do stoichiometry with the balanced equation, we can convert any species in the equation to another species. And so we already know the moles we used using math of how much known it's going to take to react with all of our total unknown. And so using the coefficients, mole-to-mole coefficients, we can make a conversion factor and convert moles of known to moles of unknown. And then by knowing how many liters of unknown we started with, and the reaction, we can divide it by liters of unknown, and we have molarity of unknown. So let me write that on the board. That's essentially what we're doing. In our titration, we're really coming up with what's called an endpoint. Our endpoint is estimating the equivalence point. So it might not be exactly the equivalence point, but it's going to be really close, so all intended purposes it'll be fine. Okay? Because usually we're going to have some indicator that will change color for a pH or something like that. And we're not going to go into theory, that's Chem 122, about the steepness of the curve at the equivalence point. So it really doesn't matter if you're a little bit off because it's so steep. The volume change is minuscule. So here's what we're going to do. Let's say we have a bottle of hydrochloric acid. Okay. It's a real old bottle and the molarity rubbed off, so we don't know the concentration of the HCl. So we're going to do a titration of this so we can figure out what that molarity is and relabel it. So we're going to take our burette. We're going to take a 50 milliliter burette. It's going to say 0 at the top, 0 milliliters. And there's going to be a 50 line down here. And there'll be like 10, 20, 30, 40, 50. And then there'll be individual milliliter lines. Okay? And we're going to fill this with our known sodium hydroxide solution. So we're going to fill this with 0.09962 molar NaOH. Okay. And then in our unknown, we're going to put, where we want to desire the concentration, we're going to put it in an Erlenmeyer flask. So here we're going to put 20 milliliters, exactly 20 milliliters of our unknown HCl solution in this Erlenmeyer flask. Okay, exactly 20 mils. So this is our unknown molarity. And we're going to put a pH indicator called phenolphthalein. And at different pHs, this phenolphthalein turns color from clear to pink or fuchsia, real pretty pink. And when it gets above pH 8, we'll just say about neutral, it goes from clear to pink. And that'll be our endpoint. The first drop, so this is very quantitative, that changes the solution pink, and that pink, when you swirl it, lasts for at least a minute. That'll be our endpoint. And then we know that we've totally neutralized and finished our titration. And here's our equation. We've got NaOH plus HCl goes to NaCl plus water. So this is our titration equation here. We're going to force our unknown acid to react and do a metathesis neutralization reaction with known sodium hydroxide to give us salt and water. And so initially our solution's acidic, see? And then we're going to drop sodium hydroxide in until it's getting more basic, or less acidic, and then neutral. Once it's neutral, we know we've consumed all of the HCl with our known, and we just got sodium chloride and water in our Erlenmeyer flask. And once we do that, we know the mole amounts in here are proportional to 1 to 1 to 1 to 1. See that? We know because that means we consumed it, and we're in the proper mole ratio. It's not 1 mole, 1 mole. It could be half a mole, half a mole. Make half a mole, half a mole. But that's the trick. Now, then we can do math and convert our known into unknown with stoichiometry. Okay? And so we put our sodium hydroxide in here, and it's 0.09962 molar. We made it. And we use analytical balance, so there's 4 decimal places. This is very accurate, very quantitative volumetric analysis. And so we put this pH indicator, and it says when we get a neutral solution, it's going to turn pink. But we don't want to go over it. We want the last drop to turn pink because it's very quantitative. So we put 2 drops, and there'll be a clear solution. Put 2 drops of that in here and mix it. And that'll be our indicator when we reach the endpoint, which is estimating the equivalence point. So we go ahead and drip, 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 drip. And we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say it took 23.23 milliliters when our solution went pink. Okay? So now with those data, we can calculate the unknown concentration of our hydrochloric acid. So let's go ahead and do that. And once again, I'm going to teach this with dimensional analysis and an equation. Okay, so we want to start with volume. Our known. With a known, you have the volume and the molarity. So we're going to start with volume of known and change it to liters first. So divide that by 1,000, and we get 0.02323 liters of sodium hydroxide. Okay, there's our volume of known in the burette times its known molarity, 0.09962 moles of NaOH per 1 liter of NaOH. And so now when we do this, once again, we're in moles of known. Okay? Now we know how many moles we put in here of known. See? It's volume times molarity. And now we want to convert this. I'm going to continue down here. I don't have much room. We're going to convert this to moles of unknown with the balanced equation. So you have to have the balanced equation for a titration. So we want to cancel moles of known, which is sodium hydroxide, and convert to moles of unknown, which is HCl. And it's 1 to 1, 1 mole to 1 mole. So there's our that's why it's called solution stoichiometry, because we're using a balanced equation to convert moles of known to moles of unknown. And so now this cancels. And now we're in moles of HCl. Now we know how many moles of HCl it took to get fully neutralized, where we neutralized all those moles. They're gone and they're in product. And by using the system, we know how many moles that is. And now we're doing the equation. We're really doing an equation here. Let me erase this. My equation I'm doing is molarity of unknown. Here HCl equal. I'm doing an equation. So this is my numerator. My numerator, I've got moles of known. See that? With two-step dimensional analysis. And now I got to put in a denominator. And so I'll just put 1 over 0.020000 liters HCl. And I know this because that's how much I put in the Erlenmeyer. I determined that very accurately and dumped it in the Erlenmeyer flask. 20 mils exactly. So now I have moles of HCl per liters of HCl, and that's the definition of molarity. See? So I do it on my calculator. So let me get my calculator. And I'm going to go this times this divided by this. And that'll be the molarity of my unknown to four significant figures. 0.02323 times 0.09962 divided by 0.02, enter. And I got 0.1157 molar HCl. Oh, now I know the concentration of my unknown acid. It's 0.1157 molar. And this is super accurate if you have good technique. So once again, a titration allows you to calculate the concentration of an unknown. Okay? And it doesn't have to be acid-base. It can be a redox reaction with a different indicator to show you when you get to the end point. But the most common one's an acid-base titration where you determine the concentration of an unknown acid or an unknown sodium hydroxide, where you have your known would be HCl. Okay? And you'll notice this is a monoprotic acid, so that's why this equation was 1-to-1, because one hydroxide neutralizes one proton from the acid. So now let's do a titration where the acid's diprotic. Okay, let's do another titration problem. And now let's get an equation. Our known's going to be sodium hydroxide again, but we want to know the concentration of an unknown sulfuric acid solution. So we're going to do a neutralization reaction again, and here we're going to get sodium sulfate as our salt plus water. But now we have to balance this. We need a 2 here, and now we've got 4 hydrogens on this side, 2 times 1 plus 2 more. So we got to put a 2 over there. And now I think it's balanced. It is. So now it's not a 1-to-1 ratio. It takes 2 moles of hydroxide or 2 moles of sodium hydroxide to neutralize 1 mole of our unknown. So we're going to do the same math, but instead of 1-to-1, it's going to be 2-to-1 when we do our stoichiometric ratio. 2 moles of acid per 1 mole of this per 2 moles of this. So let's do another problem. Let's say we have H2SO4 this time, and that's our unknown. And we got the same molarity of NaOH. And so we put that in our burette again. And once again, we're going to have 20 mils exactly of H2SO4 of sulfuric acid. We're going to put our 2 drops of phenolphthalein in there. Start out at 0 with our 0.09962 molar NaOH. And let's say it only took, our meniscus was 8.62 milliliters of NaOH. That's how much NaOH we used to turn the solution pink to reach our endpoint. And now we can use the balanced equation because we know the moles of sodium hydroxide and the moles of sulfuric acid are in the same proportion or ratio to 2-to-1. There'll be twice as many moles of sodium hydroxide to sulfuric acid because there's no excess reagent or limiting reagent. Okay? So now let me erase this so I have nice room to do the calculation. So let's write over here 8.62 mils of NaOH were required. And we started with 20 mils again of H2SO4. And remember, without a balanced equation, titration means nothing. We got to have the balanced equation. So once again, we start with, we want to go moles of a known, convert to moles of unknown, divided by liters of unknown. We got molarity of unknown. So here we've got molarity of our unknown, which is H2SO4, equal mils of known. We'll change it to liters. Divide by 1,000, and you get 0.00862 liters of NaOH. Let me write this so I have room. Times by its molarity will give us moles. And the molarity is the same, 0.09962 liters NaOH per moles. That's moles per 1 liter NaOH. And that cancels liters and goes to moles. That's where we always want to get with titration, moles of known first, and then use the balanced equation to convert that to moles of unknown with the ratios. There's 2 moles of NaOH in our balanced equation per 1 mole H2SO4. So that's stoichiometric ratio. See, this is volume times molarity gives us moles of known times the stoichiometric ratio gives us moles of unknown. Divided by, this time I'll just divide it instead of times 1 over, same thing. The initial volume of the unknown. It's the initial volume we started with, not the final volume of titration, but the initial volume, because that's the concentration we're trying to find in the bottle. Liters of H2SO4. And now we have molarity of unknown. Dimensional analysis in the numerator, we have moles of H2SO4 per liters of H2SO4, and that's the definition of molarity. So now we get out our calculator, and writing it this way, you go this times this divided by this divided by this. Because here, whenever you go below a line, you're going to push the divide sign. And we're going below another divide line, so we push the divide again. So in my calculator, I'm going 0.00826 times 0.09962 divided by 2 divided by 20 equal. See, those are the keystrokes on your calculator. So 0.00826 times 0.09962 divided by 2 divided by 20 equal. And I got to do that again. I pushed it wrong. My answer doesn't make sense. 0.00826 times 0.09962 divided by 2 divided by 0.02. I divided by 20. Enter. Now this one looks a lot better. And so that equals 0.02057 molar H2SO4. So the concentration of unknown acid is 0.02057 molar H2SO4. Same logic, same equation, but here it's 1 to 2 because our balanced equation, it takes 2 moles of this per 1 mole of this, because this is a diprotic acid. We have to neutralize both of these protons, moles of protons. And so in our next lab, when I come back from surgery, not next Thursday, but the next Thursday, we'll do a titration. Okay, each student will get to do their own individual titration. I'll give you an unknown concentration of hydrochloric acid, and I'll give you some known sodium hydroxide, and you'll get your own burette and your own your own burette and do your own titration with phenolphthalein in it and get the last drop that turns it pink. We'll demonstrate that. And then you'll turn in your concentration you calculated. Okay? Okay, we're now done with chapter 4. So you've learned a lot of math in chapter 3 and 4, and it's such basic chemistry, you have to know it really well. So you really have to work on your homework, not just once, but go over your homework problems, your lecture notes, your quizzes that we're going to have on those chapters, and learn the math and the concepts real well, because it's very basic chemistry that's foundation for further chemistry, especially if you're going to take Chem 122. A lot of chapter 3 and 4 is very basic knowledge to do quantitative chemistry in Chem 122. And then if you're not going to take 122 and go, but you're going to go into allied health, some field, now you know concentration of ions in solution, be able to calculate the molarity, etc., which is really important. Okay, good luck in your homework, and we're done with chapter 4. So this is where I'm going to end the lecture for next week. We don't need to go into chapter 5. Our next exam will be over chapter 3 and 4. Okay, good luck.